We are the NEUBIAS Academy, if you haven't heard about us from before today. So we started in April this year. We had actually now already 21 webinars. We had a huge interest. We had like over 10,000 registrations and recorded videos on YouTube that you can find on the NEUBIAS channel. There we collected over 27,000 views.
Hi everybody. So I'm going to share my screen. Okay. Okay, I think this is the first time I'm sharing my screen. I should have. Where is it? Where is the button to share the screen?
The green button at the bottom in the middle.
Oh yeah, that's quite obvious actually. Thank you. Okay. Okay, hope you can see it. Is everything okay?
Yes.
You can see it? Okay. Welcome everybody, and thanks to this the organizer of NEUBIAS Academy. It's a really nice initiative, and I hope it will continue for a long time. So in this second part, I will give some details about the statistics to analyze the spatial distribution of objects. And objects are quite general. This can be in any type of microscopy and also for localization in SMLM, but this is like more a general framework. So my name is Thibault Lagache. I'm a researcher in the Bioimage Analysis Unit at Institut Pasteur. The head of the unit is Jean-Christophe Oliveau-Marin. And everything that I will show you today about SODA, the plugin we developed, is available in Icy, a bioimage analysis platform that is free, open source, and can be downloaded through this address. So I will just give again actually a general outline to explain where we are going from a colocalization problem to a point process and a spatial analysis problem. Then there will be a second part specifically dedicated to this spatial analysis of marked point processes. And at the end, I will give you an example of some analysis we did with Lydia Danglo, who is also here today, to analyze the spatial organization in three-color structural illumination microscopy, just to show you can map the organization of synapses at the entire neuron level. So I think that you have understood that to do some colocalization, so colocalization actually it's not easy, it's like a pipeline. And so typically a first step when you do such type of pipeline is to at least decrease the noise and sometimes detect the object or the localization of your objects. And then based on this, there are quite a few standard approach, like the correlation between extracted pixel or signal, the overlap of the mass that you can detect, or distance-based approach. So for those of you that have watched the webinar of Fabrice Cordelier last week, he talked about the first order statistics, where you look at whether or not the center of some objects are inside the mask of the others. And more generally, there is a lot of distance-based, second order distance-based approach. In those approach, you are going to look at the distance between neighbors, quite generally. And then this is, let's say, the most difficult part is to interpret and to give a statistical significance of your results, because you can more or less always observe an overlap or a correlation between signal. But does it mean something? And to answer this question, I think this is the most difficult question to answer. And most of the time, what you can do is like to shuffle your signal, or let's say to randomize your localization, etc., to extract some p-values and statistics. But that's not really easy. And so this was just a general overview of like a colocalization pipeline. And that's good. Many techniques have been developed. And as you have observed with the previous part of Florian, all these approaches are being questioned with the introduction of super resolution microscopy, because now we have access to the localization directly of objects, or even more generally, we have before the yellow, let's say it disappears because we have an increased resolution for the red and the green objects, and there is not so much yellow right now in your images. And so this is really the sensitivity of many methods to the microscope PSF. I think it's really a problem, and this explains some way, in a way, the development of the object-based techniques, that you're going to try really to localize your objects or your localization directly in SMLM. And then you're going to directly work on these objects. Because otherwise, for example, if you look at the overlap or the correlation of signal, you can obtain completely different results depending on the microscope you're using. And the second issue when developing a colocalization analysis, and this issue is being more and more important right now, again, with also the increased resolution, is the contextual interpretation of what you observe, because typically two objects or more can be close, and this sometimes have no significance at all, because it is really, let's say that it is really significant if the space is empty. And this is something that Florian showed before, that really depending on the context and the background of your field of view, the proximity can have a lot of sense or not. And this is exact same thing that having, if someone is really close to you in an empty space, it's much more frightening than being in the subway, typically. Okay. And so all this small introduction was to justify the use of a very general mathematical framework, the marked point processes, to analyze the spatial relations between objects with some robustness. And just before, we have introduced the term coupling to more generally look at the distance between objects, because you can have objects that overlap, but with increased resolution, clearly many objects are not completely overlapping or not at all, but still there is a spatial relations between them. So, and this spatial relation can be a direct interaction, or the co-presence of molecules in a larger complex, or in a larger organelle, or for example, the synaptic apposition. And the common thing between all these situations is that you will have a significant spatial relations at some distance between different objects, and not specifically like overlap or something. So this is something that is more general and that has a lot of sense for a super resolution microscope. And then how you can go from pixels to objects. So in many cases, when you image molecules, these molecules are subdiffractive, meaning that their size is, let's say, below the resolution of the microscope. So typically what you observe is the PSF of the microscope, or a small object plus a big halo of the PSF. So typically you will have a lot of objects that you can segment with different techniques, like a pure Schweitzer or something that is more robust, like a wavelet analysis or convolution with a log Gaussian. And at the end, you will have like segmented objects with a given shape, a given color, and a given position. And from there, you can represent your objects in your field of view as a collection of object with a position, a point, and a mark, which will be, for example, the colors, the shape, etc. So typically, each image can be seen as a marked point process representation. And a marked point process, this is just a stochastic process, meaning that what you observe is the realization of some stochastic processes. And what you want to know if, for example, if the marked point process that is green and the marked point process that is red, are they related and at which distance? And I forget to say that typically the localization in super resolution microscopy in SMLM are per se some marked point processes, because typically you have a color and a position. And so this is an example of some synaptic molecules that have been imaged with 3D stone by Lydia Danglot at the so in French, Centre de Psychiatrie Neurosciences, Neuroscience and Psychiatry Center in Paris. So now this is the second part. So we have a good representation of the objects, let's say the position in our field of view, but what can you extract from this? And this is like the second part, this is how you analyze spatially this marked point processes to extract reliable information. And there will be some equations for people that are interested in. If you are not interested in the matter, in the statistics, you can just skip it. So just before that, I will give a very short review, and this is quite similar to what Florian just presented, but just to give, to really set the idea. So typically when you have object or localization, the first idea is, let's say, to come back to some things that we know and to look at the correlation or the overlap between molecule clusters, or at least between areas with high density of molecules. And so as Florian presented, this area, this dense area can be segmented with dbScan or some replay dependent functions. I forgot the name. Or here, this is also a replace related function in this in the article of Rossi and al, where you have so you have some dense region, and then you're going to look either at the correlation or the overlap or the correspondence in a Voronoi diagram. So there is a lot more to speak about all these techniques, and I refer to part one. And there is a second strategy. So my classification is a little bit different from the classification of Florian, but in this second strategy, this is a coordinate-based localization that he really described. But more generally, this type of strategy, I call this like the single object, and the object can be localization or even a pixel, because we can have example of such techniques like more than 20 years ago in confocal microscopy, mapping of co-clustering. So the idea is to look at each pixel or each localization and look around if there is any like co-clustering, high density of the two probe or the two colors. And these two techniques are, I mean, they are interesting. And let's say that they look at local properties of signals. And these local properties, let's say this is more or less co-clustering or correlation of high density between signals. And the third strategy that we have developed, and especially it was especially useful, at least for us, because we looked at synaptic apposition, and for the synaptic apposition, like the co-clustering or the correlation of signal, in most cases, is going to fail, especially in super resolution microscopy, because sometimes you don't have any spots that overlap or that correlate. So we developed something like a bit more general from the distance point of view, and we decided to really analyze statistically the distance directly between objects. And so if the distance is 0, this is the, let's say, the overlap. But more generally, how you can extract information from the distance. And for this, you have to first characterize the distance. So this is the first equation. Right now there is 3-4 slides where I'm going just to enter into the detail, or you can extract statistical information from the position of the different object and the distance between objects. So first you have to quantify the relations at different distance between objects. And a very well-known and widely used process is the replace function, or here this is something that is related to the replace function. So the idea is to take, for example, the first object, the green one, and to count at different concentric radii the number of molecules that are going to fall into the different annulus, or in 3D, this is in the different sphere around the points. And so you will have a number. So for example, you will have that, oh, I have a mean number of 3 molecules around at a distance comprised between 4 and 5 pixels. Okay, so what can you do with this? And this is the main part, is how can we characterize this distance related to some null hypothesis? So here the null hypothesis is that, okay, everybody is random, especially the second population. And so under this hypothesis, how much do I expect to have molecules in each annulus? And this is what is important and interesting, is in which annulus I am observing a significant accumulation of objects, meaning that there is a spatial relation at this specific distance. And this is where is coming the statistical analysis of this replace function. And so quite rapidly, we have found that the expected number of objects under the null hypothesis of randomness inside this annulus is just a Gaussian. And so we just need to compute the mean and variance. So it's not completely easy. The mean and variance is going to depend on the molecule density, the surface of the field of view, and some boundary correction, because for points or objects that are close to the boundary, we expect less neighbors, and the interactions between green objects that are going to share some red neighbors. And when you take into account all this stuff, you can, so this is the second slide with some formula, you can derive the expectation, the mean number of molecules that you expect in each annulus, which is going to be proportional to the surface of the annulus, and the variance. So the variance is going to depend on the mean, the boundary corrections, and a big term in blue, which is going to account for this the annulus intersection between the different green points. So this is an interaction term. So it's quite complicated, but at the end of the day, you have a zero mean and unit variance variable. So in each annulus, you expect, if there is no coupling, that each number, each reduced number of molecules in each annulus is going to just follow a standard Gaussian law. And then you can have, and this is what is interesting here, is that you have a multi-distance analysis, because you can then have a Gaussian vector in the different annulus around your green objects. And but once you have, like, let's say, Gaussian vectors with zero covariance like this, it's really easy to extract a lot of information. So for example, you can compute the p-value of the observation. What is the probability that what you observe is due to chance? And the other question is, okay, what is the number of really coupled objects and single objects in my image? So if you look at the maximum value of this vector, you can very easily compute the p-value. So there is a formula with the maximum value, and n, this is the number of annulus, big N. So you have a close formula for the p-value of your so the probability of observing something by chance. And then from this, you can detect the annulus that are far above a statistical threshold. So the threshold is a function of the number of annulus. And this is like the universal threshold that is commonly used in image analysis. And then you can really detect the rings where there is a statistical accumulation. And when you count the number of expected molecules in these rings compared to the expected number of molecules or spots or objects that would be there just by chance, you you compute and you have a robust estimation of the number of coupled objects at each distance. And so let's say that at a given distance, I have an object. I know that at this distance, I have a given number of coupled objects. I have a given number of objects that should be there by chance. Then I can compute the probability that this specific object is here by chance or not. And so typically in an analysis, if you expect, let's say, one object and you have 100, it means that you have a probability of 99% of chance that each object is here through the coupling. And then you can do a lot of, from this, you have a lot of information because you can compute the mean coupling distance, the mean number of coupled objects at different distance. So you have a lot of information, and this is a very versatile tool because you can use it with localization or segmented spots and at different distances. So I'm just going to show you what we did with this tool. And so we analyze the coupling between three color spots. So in blue, Homer, and PSD95 in red. So these are two postsynaptic molecules. And we look at the apposition with some synapsin in green, which is a marker of presynaptic vesicles. And so here I just give you an example of what we can observe in wide field and structured illumination. Just a remark, you can observe that the big spots that can be observed in wide field are clearly refined in structured illumination. But more than this, we can see small spots with structured illumination that could not be seen in wide field. So this is also something that is interesting here. And so this is more or less the same information. So this is an example of the PSD and synapsin and Homer in the different modalities. And then because we had like 10 images of a raw neuron, in each image we have thousands of spots. And so we wanted to run a statistical analysis and especially do this automatically and robustly. And this is where we went from the microscope and the images to the analysis through the Icy software. And the Icy is really well suited for this type of batch analysis because you have a lot of tools to automatize your analysis and typically open the files, run the analysis on the image, get the results, and do it again as long as needed. And at the end of the night, you have for example, an Excel file with all the results for 100 images, and then you need to work. And so this is exactly what we did. We designed a protocol to segment the neurons, detect the spots in the different colors, analyze the coupling between color 1 and 2, 2 and 3, 1 and 3, then integrate all this information and get a lot of statistics, or how many objects are coupled, at which distance, what are the size of the spots that are coupled, etc. So I'm just going to run a small videos that I recorded on my computer, which is okay. How you can do this with Icy. So you have to download Icy, you have to download the SODA 3-color online protocol. Then this protocol is already online, so you just open it and it charges with a lot of links. So a protocol is a series of blocks that are going to compute a lot of image analysis blocks. And the links is, for example, when you detect spots, to link the spots to the colocalization analysis, etc. It's really like doing some plumbing, I think. And so first series of spot is really like the general parameter. What are the thresholds you're applying to detect your spots or your mask? Then there is 3 SODA blocks to detect the coupling between color 1, 2, 2, 3, 1, 3. And the remaining is really to extract, okay, which spots are single, which spots are coupled only with 2, 1 only with 2 and not with 3, 1 with 2 with 3, etc. And export all the results in Excel files and images. And so at the end, so after, like for example, for a raw neuron with 10,000 spots, I think it takes something like a few minutes, maybe 3 minutes. So it was for 10 images. And so at the end, you have a lot of Excel file. So here this is an Excel file with all the coupling data at the different distances. So each line of the Excel file is the results in one annulus. And then you can combine the information for the whole annulus. And you have also images that you can just drag and drop in the IC software and observe the mass, the region of interest that are for single molecules. So single molecules is, for example, 2 without 1, without 3. Or here I'm going to underline 1 with 2 with 3. So these are the homers that are with PSD and with synapsin. So these are the three-parted synapses. Also the same with synapses that are in trio. And so I'm going just to show you where are the synapses with 3 molecules. And above that, we have, for example, synapses with only 2 spots, PSD and homer, or some with only homer and synapsins, etc. So it's at the end we have a lot of information, and then you can do a lot of graphs and having a lot of information. So this is just a summary. We observed that typically the spots that were alone were smaller, and then a lot of them were just a couple. So they were a little bit bigger, but smaller than the spots that were in a trio. We had the histogram of the distance because you remember that we have the information of the coupling at each annulus. So we have the information of the coupling distance and how it is distributed. And so, for example, here we observe that the distance between PSD and homer, so this is in red and blue, is much lower than the distance between PSD or homer from PSD 95, or from synapsin, sorry, because synapsis is on the other side of the synapse. And what is really important is that we can see the arrangement of the synapse with the synapses that is in face of the PSD 95. So the PSD 95 is really at the PSD, and the homer is slightly behind and slightly like on the side of the synapse. And this is something that has been observed with very few examples in electron microscopy. And I don't remember, but yes. And the next slide is that actually what I show with structural illumination and spot, etc., is completely also applicable to single localizations. So you have to segment a region of interest. So this is something that we do. So we segment the presynaptic button by looking at the cluster, and actually we use a DB scan. And inside the presynaptic clusters, we look at the coupling between single molecule localizations at different distances. And we extract molecules that were single or coupled. So here between synapsin and Viglet. So these are 2 markers of presynaptic molecules. And what we observed is that they were indeed coupled with a mean distance of something like 60 nanometers. So the size, more or less than 40 nanometers, so the size of a synaptic molecules, and a stoichiometry that was in line of what have been observed with mass spectrometry. Okay, I'm already at the conclusion. So as I show you, there is a lot of standard tools, but these tools are, how to say, most of standard tools are not really efficient for increased resolution and also for localization-based microscopy. And more than that, it's really hard to give an interpretation of your results. What is the probability that what I am observing is due to chance? And can I map which are my localization or my objects that are single or coupled? And so this is why we have developed this statistical analysis at different distances and implemented it in IC to really get statistical information at different distance between different objects. And this works in wide field, confocal, SIM, or localization-based microscopy in 2D and 3D. And so the acknowledgement, so I mean, we acknowledge Institut Pasteur and all the other like CNRS, ANRs that are financing the lab and this research in particular. Centre de Psychiatrie and Neurosciences, this is the center of Lydia that is really helping, and especially through the imaging facility. They have a great imaging facility. Everything is available in Icy. Icy has a strong support from France Bioimaging. And I really thank NEUBIAS for the invitation and for, what they do, because really, they really build a community around bioimage analysis, and that's really nice. So from here, I would like to thank you, and I'm going to stop talking and listen to questions if there are some questions. Thank you.
Yes, so we have some questions. Some of them have been answered online, but the first question was, can you have a specific file format, and can you use whatever CSV file to load your localization?
No, there is no format. Typically you're uploading an Excel file, and so there is two types of protocols in Icy. There is a protocol for general imaging where you detect spots, etc. And there is a protocol that is really dedicated to localization microscopy. And in this protocol, you have a first series of blocks. So everything is explained online with the documentation, but you have a series of blocks where you're going to choose the number of the column that contains the localization in X, the other one in Y, and the other one in Z, if you are in 3D. And you have even a column where you specify the number of photons, and you can specify that you just want to use the localization with more than a given number of photons. So this is a series of blocks that is really going to specify the column of your Excel file for the localization. Hope I'm clear.
Thibault, can you just give the name of the protocol you're talking about?
This is...
Is it the STORM 3D?
Yeah, STORM 3D SODA. Yeah. And there is a STORM 2D SODA. And there is, so in the protocol STORM, so you have to specify the column. And I talk rapidly, but you also specify how you are going to build your clusters. And in Icy, what we have is the DB scan. So you have to specify some parameters of the DB scan to segment the clusters, because SODA is going to look inside the clusters and look at the single localization inside the segmented clusters. So the approach is completely different from the other approach in localization by microscopy, where more or less you're going to look at how the clusters interact or overlap or correlate. Here you segment the cluster and directly look inside at the molecular level, at the single molecule level.
There is one more question, and that says, for the formation of the annuli for non-circular objects, does it match the contours of the objects, or does it always assume circular shells?
So actually, with what I presented today, it was really based on the center of mass, so everything was circular. But we are now generalizing the approach and consider the shape of the object and the contour, and then the annulus is no more an annulus, but is more an isoline that is following the contour of the object, and that is expanding from the contour of the object. And this can be found in a recent publication. So first author is Suvadip Mukherjee, and this has been published in Signal Processing Letters in 2020. And the plugin will be available very soon with all the documentation.
Another question is that can localization error be incorporated in the two-color analysis?
It should. This is also in progress. So yeah, it should. Because right now, to model the colocalization or the coupling, we model this with some point processes, and so a point process is going to be coupled at some distance. But definitely, we are now thinking about how to incorporate the localization error in the computation, and also the resolution, because typically from the resolution, you cannot have 2 points that are closer than the resolution limit, even in SMLM. So typically this also complicates the analysis. And so we are working on this theoretical aspect.
Another question is that how do you load your SML data in Icy? So I think you partly answered in the previous question.
Yeah.
But
yes, typically, so the basic file is an Excel file with the localization. And then most of these tools are available in the protocols in Icy. And so there is a series of blocks where you're going to specify where your file is and which columns of your Excel files are containing the X, Y, and Z of your localizations.
yes, so you do not need to reformat your data. You just have to load it and create the column.
Yes. Yes, there is no reformatting, but at the end you need the localization in CSV or Excel file.
Okay, I think there is no more question, or maybe it will come.
So it looks like we don't have any other question. Before you leave, just 1 more second. I need to send you the link to the survey for today's webinar. It's really important that you answer this survey and help us improve our webinars. So here, just a minute. Yeah, thank you, Rocco. So I hope you enjoyed this webinar today on advanced methods of colocalization with Florian Lebet and Thibault Lagache. I want to speak the 2 speakers today again for their great talk. And yeah, please complete the survey that Rocco just sent to us. We recorded the session and we will post the video on YouTube soon, and also the answers to the question you asked during the webinar. Yeah. So thank you.
Thank you for organizing.
Thank you. Bye-bye.
Bye.